Introduction to something called exponential functions. And it starts off by saying, let's say that we have a microbiologist who's studying bacteria colony on a nutrient-rich petri dish. She observes that the number of colonies on the dish for the next 3 hours. Okay, so she has a certain amount. Now, if you look over here, this says the hours, and this is the number of colonies. At 0 hours, this is literally means like right now. Okay, there is just one colony. So that means that at the beginning, when she first started this, there's just one colony. After 1 hour has passed, there's two colonies, right? So what's the increase from one to two? Well, it's just plus one. And if we were to then look at 2 hours, well, now there's four colonies, right? So to go from that two to that four, we added two, okay? And then after 3 hours, there's eight colonies. So if you were to go from four to eight, that's four. Now, if you've already done a linear functions, you should automatically see that this right here is kind of a problem because linear functions, right? That's these guys right here, linear functions, they only increase or decrease by the exact same amount every single time. So this should have been going up by like plus one, plus one, plus one. Now these are three different numbers, and so we cannot represent this scenario using a linear function. Rather, we need to use something called a exponential function, and instead of increasing or decreasing by through or like by adding or subtracting, instead we need to find a different pattern. Okay, so how else can you go from 1 to 2? Well, you can multiply by 2, right? Because 1 times 2 is 2. And if we take the same pattern here, 2 times 2 would also give us 4. 4 times 2 would give us 8. So we can see now that there's a pattern. It's not the same thing as linear, but we're going to be multiplying by the same amount every single time. So our y values, these are y values right here, and these are x values. Our y values or our outputs change by multiplication each time. Okay, so to take a look at that is, what's an exponential function? Well, an exponential function is usually defined as anything that takes this form. Okay, and we're going to just break down what each piece means. So our y's, this is our output. Okay, our output values. A, this represents the initial amount or the initial value, okay, when, and this is the important part, when x is equal to 0. So that means like right when you first start off, and I'm just going to go back really quickly here. See, when we first started off, x always represents time, and so at 0, when x is 0, this was our value, our initial amount, and we started off with just one colony. Our b, okay, this is called our growth rate. Sometimes it's actually known as a multiplier. Okay, because again, with exponential, you're always going to be multiplying by a certain amount, and x will be our input. Okay, now for the most part, mostly, I should say, it's like a time, right? So I should say mostly a unit of time. Now that's not always necessarily true, but if you're like in algebra 1 or algebra 2, the majority of the time we're going to be working with some kind of time interval, like seconds, minutes, hours, days, months, years, anything relatable to time, right? And then a good question that I always get is, how do you know if you're working with an exponential function and not something like a linear function, which most people spend a lot of time on? Well, you know that because the x, so the x value or variable, okay, will be the exponent. And that's really all there is to it. Right? So like when I have y equals, let's just make up something, right? Let's say the 4 to the x, okay? Well, you'll see there that the x is in that little tiny exponential space above the 4, and that's how you know it's an exponent. It's an exponential function because literally the x will be the exponent. All right? Okay, so let's just take a look at an example really quickly. So here we have the general form. Okay, this is the general form. All right. And an example is right here. Now, another way that we could write this is we can write this the y is f of x, and sometimes you'll see that. okay, a times b to the x. And if we take a look at what we have here, we have f of x is equal to 2 to the x power. Okay, so this right here is going to be our output. All right, this right here will be our input. And if you'll notice, you see how the b is being raised to the x power? Here, this 2 is being raised to the x power. So this is actually our b value. Okay. Oh, in this case, we're going to call this a base. Now, I know in the last slide I had called this a growth rate, a multiplier. There's so many different names for it, but the most popular name is a base. Okay, and this a value, it's not like imaginary, right? There is an a value. If I were to write this over here, f of x is equal to 2 to the x. Well, below that, I'm going to write what the general form is. And what you'll see now is that we have this little gap here, right? So now what can you multiply any number by that even when you multiply by this number, it stays exactly the same? And that number would be 1. So here our a will be 1. Okay, so now to go through some of these things here, our initial value, okay, the initial value is always going to be our a. If I just go back really quickly to the slide, our a is going to be the initial amount when x is 0, but always remember that this is going to be your initial value. So this is going to be 1. Our base is our b, okay, b for base. This would be 2, all right? We also have our growth factor here. This is also going to be 2. And we'll talk about domain and stuff that later. So what we're gonna do is let's just try to fill out this table, okay? Now what this means is we're going to take every x here and every y here, and we're gonna figure out, well, if I plug in an x, what would the y be? And before we start dealing with any of the negatives, let's just first do some of the positives, okay? Now if you have a calculator, that's fantastic, but let's just try to see if we can do this by hand. So here is our equation, 2 to the x. If we were to start at 0, it's this one here, f of 0 means that I'm plugging in a 0 everywhere that we see an x. So this right here would be 0. Now 2 to the 0th power, or anything to the 0th power, is actually just 1. And that's a good math fact to really remember that. So anything to the 0th power will be 1. Okay. Then we have now, if we have f of 1, okay, now that's this one right here, we're going to just substitute this 1 for the x. Okay, now what is 2 to the first power? 2 to the first power is we're just taking 2, raising it to the first power, and it just simply stays at 2. So this would be 2, right? What about now if we had, and we'll do this right here again, f of x equals 2 to the x. If we have a 2 here, okay, we're just substituting everywhere that you see an x, we're going to substitute with number 2. Then this becomes 2 squared. Now, if you were to expand this, 2 times 2 equals 4. So then this would be 4. Okay? Why don't we try out for f of x if x is equal to 3? This would simply be f of 3 equals 2 to the 3rd power. So what this really means is you're taking the number 2 and you're writing it out 3 times, and then we'll multiply them. So 2 times 2 times 2 gives you 8. All right, and notice that I actually did not do these yet. This is a little bit more, it's a little bit harder to think about, a little bit more conceptual, but let's just see if we can explain it this way, okay? Now, if I start here from the bottom, to get from 8 to 4, we can think about it as dividing by 2 or multiplying it by a half. Now, I'm just going to say divided by 2 for now. Actually, I don't like that. We're going to say multiplying it by a half. Okay, so we're going to multiply this by half. So to get from 8 to 4, I multiply by a half. It's like saying half of 8, right? Then from here to here, what is half of 4 gives you 2, right? Then half of 2 gives you 1. Now what is half of 1? Well, 0.5, which is just a half. And what's half of a half? So if I were to draw a rectangle here, here's half. Okay, now what's half of a half? Bam. And if you were to just make the same indentation there, you'll see that this is just a fourth. Okay, now the mathematical way here is that when you have 2 raised to a negative power, what you're going to do is you're going to, well, the way that I do this is I actually take this 2 to the negative first, I put it over 1, all right? And then once you do that, you're going to flip it. And in the process of flipping it, this will become a positive. So this becomes 1 over, see, notice I'm flipping it, 2 to the positive 1, and 2 to the first power is just 2, giving you the half. Same thing for the 2 to the negative 2. Okay, we're going to put this, oh, I wrote that way too small. 2 to the negative 2, put over 1. Okay, you're going to flip it, and in the process of flipping it, this becomes a positive. So 1 over 2 to the positive 2, which is 1 over 4, giving you 1 over 4 there. All right, now if we were to graph this, how would that look like? So a little bit more tricky to graph this. Let's start with 0, comma 1. Okay, we always want to start at 0, comma the y value, then 1, comma 2, then 2, comma 4, okay, 3, comma 8, and let's go back and see if we can fit this in. Okay, so negative 1, a half, negative 2, a quarter. And if we were to connect this, notice it's not a straight line anymore, right? We're no longer dealing with lines, but this is going to be a curve, okay? And this curve actually extends, but never passes, it never passes this x-axis. Okay, it never passes this x-axis. So what we have is a curve, and this is called an exponential function. Exponential function. All right. Now, last thing I just want to go through really quickly is domain. So domain really pertains to the x values. Okay, so think about now as you're moving to the right. Okay, how far to the right can you go? Now I know that this graph looks like it's cutting off around here, but it's really not. If we were to extend it all the way over and over and over and over and over and over and over, it's actually going forever. Okay, and I should really say this way, it's actually going forever in the right direction. So we say that this is going all the way to positive infinity. And then on this side, okay, we're going all the way to the left. So we're going to all the way to the negative infinity. And so our domain would just be negative infinity to positive infinity, otherwise known as all real numbers. This is the term that we use when it includes every single number on the coordinate system from negative infinity to positive infinity. Okay, all right, that's it for this one. We'll do a lot more examples. We'll actually go into depth with the lessons, and I hope that they help you out.